Hello, my name is Beth Dixon, and this is a video series based on Vicki Borlaug's PowerPoint presentation on proportions. Note, this is designed to be viewed after confidence intervals and hypothesis testing on the mean, which may be a slightly different order than your teacher has covered the material. I wish to thank Mrs. Borlaug for allowing me the use of her PowerPoint to make this set of videos. Here is a summary of the topics that we will cover in this set of videos. When can the binomial distribution be approximated by a normal distribution? Looking at the graph and deciding when a normal can be used for that binomial distribution. We'll look at confidence intervals for proportions. We'll look at determining sample size for proportions, which may be optional and may not be covered in all courses here at Walter State. And we will look at those without any estimate for proportion and those with an estimate for proportion. And lastly, we will look at hypothesis testing for proportions. What is a proportion? This is the first question that we need to answer as we start this set of videos. Looking at the fraction 4/5, we have two equivalent ways of writing 4/5. We have its equivalent decimal form, 0.80, and its equivalent percent, which is equal to 80%. Those are three equivalent forms of that number, as the fraction, as the decimal, and as the percent. 4/5 and 0.80 are considered proportions, and 80% is considered the percent. So if I said 4 out of 5 doctors recommend a toothpaste, or 4 out of 5 dentists recommend a toothpaste, that's a proportion. If I say 0.80 recommend, that's a proportion. If I say 80% of the dentists recommend, that's a percent. And it's just a wording or a definition of the words. We will also need to review some of our variables and notation that we use for this topic. For the mean, we use X bar to estimate mu. Both of those are referred to the mean, where X bar is a sample mean and mu is the population mean. And we use X bar to estimate what mu is. We use the sample to estimate the population. For standard deviation, we use S is used to estimate sigma. The sample standard deviation S is used to estimate the population standard deviation sigma. For proportions, which is what we're covering now, P hat, and that's P with a little hat over top of it is what we call it, but it's just a slightly up arrow, is used to estimate P. P hat, which is the sample proportion, is used to estimate P, the population proportion. And for the correlation coefficient, R is used to estimate rho, which is the Greek letter that looks like a P. But notice it's got a little different shape to it. And of course, since we're dealing with proportion, we're going to be talking about P and P hat. We also need to do a quick review of binomial distribution before continuing. So, as a quick review of what constitutes a binomial experiment, remember that it has a fixed number of trials. The trials are independent of each other, and each trial has two categories, a success or a failure, and the probabilities remain constant for each trial. As we continue our review of the binomial distribution, remember that we have notation and variables for the binomial distribution. N is our sample size. P is our probability of success. P is also the proportion of successes in the population. So that's why they're the same variable here, P. Q, whoops, I went too far. Q will be the probability of our failure, or will be 1 minus P. And X, remember, is the number of successes out of N, our sample size, or in our population, depending on which one we're dealing with at the time. We're now ready to do example 1. Consider the planets in a certain region of space. Some of the planets have moons and some do not. So X will be the number of planets with moons. X is a binomial and the success is the planet with moons. So we have N, P, Q, and X that we will define, and P will be the proportion with moons. Our goal is to estimate the true proportion P of planets with moons. Here is a random sample of our planets. Now this is not the entire population of planets, it's just a random sample. And X is the number with moons. You could pause and count, but there are 10 with moons, or let's just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 with moons. That leaves us 1, 2, 3, 4, 5 without moons, for a total of 15 planets in our sample. So our P hat, because it is a sample, is that there are, what is the proportion with moons? 10 out of the 15, or 0.667 in decimal form. For Mrs. Borlaug, she will round to 3 decimal places. Q hat will be 1 minus 0.667, and some of your teachers will not use the variable Q, but will just stick to listing that as 1 minus P hat, and that would be 0 minus 0.333. The estimate of the population proportion of planets with moons in the region of space is P hat equals 0.667 based on this random sample. Generally, we'll round to 3 decimal places for proportions. Your teacher may have different rounding rules than what Mrs. Borlaug and I are using for this video, so please check with your instructor for rounding rules for proportion. So our P hat is 10 out of 15, or 0.6666667. And no, I did not count to see if I said the correct number of sixes. That's not important. So rounded would be 0.667. We're reaching about the 10-minute mark, and so this is our second example, and I will pick up with the second example in part 2 of this series. Thank you for watching.